Alright, what's up guys? In this video we're going to pick up some calculus here, and in this video I'm going to show you guys how to do tabular integration. So we're asked to evaluate the integral x to the fifth times cosine of x dx. So we're going to use tabular integration to evaluate this, and let me just give you a little bit of background on tabular integration. So basically what tabular integration is, it's basically another way to do integration by parts without having to do it multiple times. So basically, if you remember in the previous videos that we've done, maybe we haven't evaluated this particular integral in other videos, but we've evaluated integrals very similar to it. Particularly, we've evaluated integrals where we have something like x raised to the second times cosine of x, or x raised to the third times cosine of x. And as you notice here, we have a product of two different functions. We have a polynomial here, and we multiply by a trig function. So when we have a product of functions, we apply integration by parts. But recall that if we have an x squared or an x cubed or something like that, we're going to have to apply integration by parts multiple times in order to get the answer. Particularly if it were the integral of x cubed times cosine x, we'd have to do it 3 times to get the answer. In this particular circumstance, we could apply integration by parts and evaluate this integral using the formula. The problem is we would have to do it 5 times in order to get the answer, because every time we apply the technique, it's just going to drop the power of the x down by a power. And so it would just go down to x to the fourth, x to the third, x to the second, and then finally down to the first power. So we'd have to do it a significant number of times to get the answer. Not terribly difficult, but very tedious. As you know, anything that's that tedious is going to be, how do I want to say, it's going to be the field for making mistakes. So the purpose of tabular integration is to make this easier. So basically, what you need to do for tabular integration is we're going to set up a table. So let's go ahead and set that up. And since we have x raised to the fifth power, we know we're going to need to get about 6 derivatives and obviously 6 integrals. So we'll go ahead and create a table here, and we'll close up the table. This column will be the u, and this column will be the dv. Okay. So one of the drawbacks, well, I don't know if it's necessarily a drawback, but one of the benefits of tabular integration, well, actually, you know what, I'll say a drawback. You still do have to go through the process of finding your u and dv, but the benefit in this particular circumstance is that it's very easy to determine what your u is going to be for tabular integration, because you want to pick your u to be something that when you constantly differentiate it, at some point you'll get down to a constant. Okay, which we know that if we take the derivative of a constant, we'll get 0. So in this particular case, notice how we have x to the fifth times cosine of x. So what would be the appropriate u here? Well, the appropriate u here would be x to the fifth, because if I take repeated derivatives of this with respect to x, I'll eventually get down at some point to some constant. And then when I take the derivative of a constant, I get 0. So x to the fifth here would be a good selection for u, which means that dv, kind of just like when we use the formula, would just be everything else, would be cosine of x, not dx, but just cosine of x for tabular integration. So why would it not be cosine of x as u? Well, I can take as many derivatives as I want to for cosine. So I'll start with cosine, negative sine, take the derivative of that, I get negative cosine, take the derivative of that, I get positive sine. No matter how many times I take the derivative, I'm not going to get 0 at any point. So that would not be a clear selection for u. So determining what the u is for tabular integration is actually a lot easier than it is with using the formula. Now, some students will say, or some people may say, well, let's just say, for example, if we're using the formula, well, you want to pick u to be this in this case, and pick u to be that in that case, and pick dv to be this in this case, and dv to be that in that case. The problem with integration, and really anything in math, I never consider everything to be all or every. No one integral is one size fits all, and you can easily manipulate an integral by just changing adding a variable, adding a constant, doing something like that, and it can completely alter the entire process of how you evaluate the integral. So for me, when students ask me, well, what's the best selection for you in DV, obviously I can give you some pointers on things to look for, but it really just kind of depends on what kind of integral you're given, and I'll actually have to look at it. But I'm always cautious of telling students that you're always going to pick this to be U or always going to pick that to be DV, because integrals can be they can be manipulated in a variety of ways and easily mess up what you thought were the appropriate selections. So the only way to get better at, in the particular case of using the formula of determining a U and a DV, is by doing various practice examples. In this particular case, it's a lot easier. So we have x to the fifth. And so basically what we do, after we've gotten down our x to the fifth, we start by integrating we take the antiderivative of our cosine here, and that will go in our first slot. So what's the antiderivative of cosine of x? Well, it's positive sine of x. Okay. And so basically what I'm going to do is I'm going to take 6 derivatives. It's going to get me down to a constant. And we're going to continue to integrate as well. So let's begin by taking some derivatives here, and it's just power rule. So this would be 5x to the fourth. This would be 20x to the third. This would be 60x squared. This would be 120x, and then down to 120. Okay. Now let's take some antiderivatives all the way down to number 6 here. So what's the antiderivative of sine of x? Well, it's negative cosine. Okay. What's the antiderivative of negative cosine x? Well, that's negative sine x, because the antiderivative of positive cosine x is going to be positive sine. But since we have a negative there, it would be negative sine x. Now we take the antiderivative of negative sine x. Well, if the antiderivative of positive sine x is negative cosine x, well, then that means that the antiderivative of negative sine of x is positive cosine of x, because two negatives make a positive. And then we just keep going. Okay. And now we're down, and we've gotten all of our antiderivatives down to this point. Okay. So that's the first thing you do. So once you've gotten the table done, the next thing you need to do is you need to change the sign on each even derivative. Or as you can see here, we have 1, 2, 3, 4, 5, 6. So we're going to change the sign on number 2 to a negative. We're going to change the sign on this fourth one here to a negative, and change the sign for this 120 here to a negative. So you do that for every even derivative that you took. So here we got x to the fifth. Now we get to multiply by sine x, or sine of x. Now we're going to need to change the sign here. So I'm going to change the sign. So it's going to be 5x to the fourth, or negative 5x to the fourth, multiplied by negative cosine x. Now, much like anything in math, as it pertains to arithmetic, if you're not careful with your sign changes, you can easily get it wrong. So please be careful with your sign changes. Again, our odd order derivatives, we leave those alone. So this would just be 20x to the third multiplied by negative sine of x. I highly recommend using parentheses. That will lessen the likelihood that you'll make an arithmetic related mistake with these negatives. So notice how, again, I'm inserting negatives for every even order derivative that we took. So we took our fourth derivative. Again, we got 60x squared, so I'm going to stick a negative in front. We're going to multiply that by cosine of x. We don't touch our fifth one, which was 120x. Well, we're going to multiply that by sine of x. And then our even order derivative here, which is our 6, we're going to make this negative 120 multiplied by negative cosine of x. Okay, so now hopefully you're seeing how everything is done. Okay, so all we have to do at this point is simplify everything, sum everything up, and add a plus c. So let's go ahead and do that. So it looks like we'll get x to the fifth sine of x plus, because we got two negatives, it's going to be plus 5x to the fourth cosine of x. Then we'll have, sorry, it's going to be a negative, excuse me, negative 20x to the third sine x, or sine of x. Then here, this would be minus 60x squared cosine of x. Then we'll have plus 120x sine x, or sine of x. Okay, and then our last one here would just end up being plus 120 because we have two negatives, so it would be plus 120 cosine x. So plus 120 cosine of x. Okay, so hopefully you're with me so far on where I'm at. Now let's just simplify this and clean this up a little bit, and we'll get our answer. So I'll actually go ahead and just write final answer. We just need to simplify it a little bit. So we'll use tabular integration to integrate x to the fifth cosine of x dx. Okay, so let's kind of group everything together and simplify a little bit here. So we're going to get, I'm going to write this as x to the fifth minus 20x to the third. And then this would be plus 120x. Hopefully you're following me on this. Okay. And we'll have our sign on the outside here. And then we'll add that to 5x to the fourth minus 60x squared plus 120. And then we'll have cosine of x on the outside here. And all I need to do is add a plus c. And that would be your antiderivative using tabular integration. Now, if you're not convinced that this is the antiderivative, much like you can do for any integral, you can always take the derivative of the result, and you should get that back out. Now, this isn't terrible to differentiate. I mean, you got some power rule going on in here, so this is actually pretty simple. It's a little bit of simplification that you'll need to do to get back to what we have in our integrand at the top, but if you do it, you should get that back out, so you'll probably want to check for that. So this is how you do tabular integration. So it seems like an easier method of when we get into a situation where we need to apply integration by parts multiple times. And it is, it's a helpful technique. But again, I don't want you guys to get so stuck on tabular integration because it does not work all the time. Because again, let me just briefly go back to what we talked about at the beginning. When we set up our table, we know when we are deciding what the u is going to be. Again, it's a lot easier to determine it for tabular integration than just for the regular by parts where we're using the formula. You want to make sure that whatever you select your u to be, eventually you can differentiate it to the point where you'll get a zero, which means you'll have to, when you take repeated derivatives, you'll have to get down to a constant at some point. And we know when we take the derivative of a constant, we get zero. So you need to be able to do that. If you can't do that, one or two things may be the problem. You pick the wrong u or dv, and again, it's a lot easier to determine what's the u and the dv for tabular integration, so that should not be an issue for you. Or you simply can't apply the method. Okay, so if I had something like, I'm trying to think of something that, let's say I had, I don't know, e to the x times cosine of x dx. Well, I can't use tabular integration for that. I'm going to have to use integration by parts for that, because no matter what I select my u to be, taking the derivative of e to the x repeated times is not going to get me down to a point where I'm going to differentiate a constant and get 0. And then differentiating cosine of x is not going to get me, no matter how many times I take the derivative, I'm not going to get down to a constant such that when I take the derivative, I'll get 0. So an integral like that you can't use tabular integration for that. So this can only be used in certain situations, and it is relatively helpful. Now, I did not learn about tabular integration until I think about a year and a half ago, maybe. I had no idea what it was. It's an easier way to do integration by parts. But again, can be applied all the time. Very similar to how, if you remember from college algebra, polynomial long division and synthetic division. Everybody loves synthetic division because it's the easier way to do it, but it can't be applied all the time because we need to be dividing by a linear term in order to use it. So kind of think of it like that. So that's how you do tabular integration. So let me know if you have any questions about it, and I will see you next time.